Write Academy. Learn it, teach it, remember it. Today we're going inside the two machines that store nearly all of the world's data, the B tree and the log-structured merge tree. They differ on exactly one question: where does a single write really go? And by the end, one question will tell you which engine wins. Here's a little mystery to start with. Two database engines on identical machines. The same disk, the same memory. We fire the same heavy stream of writes at both. The first engine drinks the stream without blinking. Watch its counter climb, tens of thousands of writes every second. The second one chokes almost immediately. Writes pile up at the door and its counter crawls. Same hardware, same data, a 30-fold gap. The whole difference is one design decision. Where does a single write physically land on the disk? Hold that question. This video is the answer. Before any machinery, picture keeping records on paper. You have two options. Option 1 is a binder. Pages in sorted order, every record on its proper page. When a new record arrives, you find the right page, erase, and rewrite it in place. The binder is always tidy, so looking anything up is quick. But every single update means finding and rewriting a page. Option 2 is a journal. You only ever write on the next blank line. A new record is appended at the end. Done. Writing is as fast as your hand can move. But finding something later means scanning back through everything, unless you now and then recopy it into sorted order. The B tree is the binder. The log-structured tree is the journal, plus a clever scheme for the recopying. Let's build the binder in silicon. The B tree is the binder, fixed-size pages arranged as a short, wide tree. A root page at the top? The root points down to interior pages, and the interiors point to the leaves where the data lives in sorted order. The tree stays shallow. 3 levels can cover millions of keys, which makes a read beautifully cheap. Say we want key 51. We touch the root and its guide keys send us to the middle. One more hop through an interior page, and the leaf has our key. Count the work on the meter. 3 page touches, that is the whole read. This is why the B tree has ruled read-heavy databases for 50 years. Now watch a write, because this is where the story turns. We insert key 47. Same walk down to the one leaf this key belongs in, and that leaf is modified in place and written back to disk. Here's the part the diagram hides. Look at where the pages actually live on the disk. They're scattered. So that page write lands at some arbitrary spot and the disk head has to jump there. Insert another key and it jumps somewhere else entirely. This is random access, and storage punishes it. Watch the seek counter climb as the head thrashes. And when a leaf fills up, it splits into 2 pages and the parent is rewritten too. One insert just became 3-page writes. Random writes can run 10 to 100 times slower than sequential ones. So under a heavy write load, this engine spends its time seeking instead of writing. That is our choking engine from the start. It moves. Never modify a page on disk. Only ever append. If every write lands right after the previous one, the disk never seeks. Watch the same track now. The head parks at the end and just slides. Sequential writes run at the disk's full bandwidth. This is what the hardware is physically best at. But hold on. A pile of appends in arrival order is unsorted. How will we ever read it back? That is the log-structured merge tree. Append now, sort in memory, merge later. The cost doesn't vanish. It moves. Watch where. Here's the write path, end to end. A write arrives, key 42, and it lands in 2 places at once. Place 1, the write-ahead log, an append-only file on disk. The record is appended sequentially, no seek, and forced down to the physical platter. Place 2, the Memtable, a sorted structure in memory. The record drops in at its sorted position, a few pointer hops in RAM. And that's it. The write is acknowledged. Essentially, every system answering a distinct count query at scale. Key 17 arrives. Log first. And into the Memtable in sorted position ahead of 42. Key 88, same dance. Now watch an update. 17 again with a new value. The log just appends, it never edits. And in memory, 17 simply takes the newer value. Old data is never touched on disk. Of course, the Memtable can't grow forever. Watch the gauge. At a threshold, commonly around 64 megabytes, it's full. So it flushes. The whole Memtable is written out in one sequential pass as a sorted file. Immutable, ordered, never edited again. A fresh Memtable takes over. And the log is truncated. Everything in it is now safe in that file. Sorted files will pile up. Remember that, it's about to matter. Now, why write that log at all if the Memtable already has the data? Let's pull the plug and find out. A fresh write comes in, key 63, into the log, into the Memtable, acknowledged, and then the process dies. The Memtable was memory. It's gone. So here's a question worth pausing on. We told the client 63 was saved. Where is it now? There. The log is on disk. It survived the crash. On restart, recovery replays the log from the start, reinserting every record into a fresh Memtable. And 63 is back. Every acknowledged write survives. That is the whole contract of the write-ahead log. Ahead means the durable copy is written before we ever say yes. Durability from the cheapest write that exists. Now the journal's bill arrives. Let's read one key back, key 51. Where is it? Honestly, it could be in a lot of places. We check the Memtable first, the newest data. Not there. That's one check. Below it sit the newest sorted files. Level 0. Each was flushed independently so their key ranges overlap. 51 could be in any of them. So we check every one. 2, 3, 4, 5. Nothing yet. Below those, the deeper levels are tidied into non-overlapping files, so each level costs one check. Level 1, 6. Level 2, 7. And at the very bottom, level 3, 8. There's our key. 8 places touched to answer one read. The B tree did it in 3. This is read amplification. How many physical reads one logical read costs? The journal pays at read time exactly as promised. Here's the rescue. Every sorted file carries a Bloom filter, a tiny summary held in memory that answers one question. Could this key be in this file? When it says no, that's a guarantee. The key is definitely not there, and we skip the file without touching the disk. Once in a while it says maybe when the answer was no, around 1 time in 100. That's the price of being tiny. Watch the same read again, key 51. The filters answer instantly. No, no, no. Almost every check collapses. One file says maybe, so we open it. Not there, a false alarm. And the bottom file says maybe, we open it, and there's our key. 2 files actually opened instead of 8. With filters, the journal's reads land within sight of the binders. Without them, this is not a production engine. Bloom filters aren't an optimization here. They're load-bearing. Meanwhile, those sorted files keep piling up and each one makes reads a little worse. Someone has to tidy. That someone is Compaction, a background merge. Here are 2 overlapping files from level 0. Notice they disagree. Both hold key 17, and the newer file carries a tombstone, the little marker that means key 51 was deleted. Deletes append too, remember, nothing edits in place. 2 fingers walk both files in key order and merge them. 17 appears in both, only the newest version survives. The old one is dropped. 42 comes across clean. The tombstone meets key 51 and kills it. Both vanish. The delete is now final. 88 comes across. And 90. Out comes one bigger file. Sorted, no overlaps, no stale versions. Reads just got cheaper. Compaction runs continuously in the background, merging downward through levels that grow roughly 10-fold each. And it has a price of its own. Here's that price. Follow one record, key 42, through its whole life and count how many times it physically hits the disk. It arrives. Once into the write-ahead log, that's 1. The Memtable flushes it into a level 0 file. Written again, 2. Compaction merges its file down into level 1. Rewritten, 3. Level 1 compacts into level 2, 4. And into level 3, 5. One logical write became 5 physical writes in our little 3-level engine. Production stores run 6 or 7 levels deep, so a record typically lands 5 to 8 times before it's home. This is write amplification. And the binder? The B tree writes each record roughly once into its page. Randomly, but once. So neither engine writes for free. One writes randomly once, the other sequentially many times. And the bandwidth compaction each sets up the one failure every senior engineer is asked about. Push a heavy burst at the log-structured engine. A batch import. A traffic spike. Flushes race ahead of compaction, and level 0 files pile up faster than the merger can drain them. Watch the count. 4 files. 10. 50. This is compaction debt. And reads must check every one of them. The 8-check read from before is now over 50 checks. Worse, compaction is working frantically, eating the exact disk bandwidth those reads need. So tail latency cliffs. A read that took 5 milliseconds now takes 5 full seconds. And finally, the engine defends itself the only way it can. It stalls. Incoming writes are paused until compaction catches up. Your write-optimized database just stopped accepting writes. On call, the signature is unmistakable. Latency cliffs every few hours, lining up with the big compactions. The leading indicator is the level 0 file count. Alert when it passes 10 and you get half an hour of warning before the cliff. Time for the scoreboard. Both engines, side by side. And let's be fair to both. First, a write-heavy workload. Fire the stream. The binder seeks for every page, watch its counter crawl. The journal appends at full bandwidth, tens of times the ingest, on the same disk. That round isn't close. Now flip the workload, reads and range scans. The B tree answers in 3 touches every time, and the neighbors on the leaf are right there for scanning. Steady, boring, predictable latency, no background storms. The log-structured engine holds close on-point reads thanks to the filters. But it's paying rent in the background. Compaction churns, and a bad day brings the stalls we just watched. So the honest scoreboard. The binder pays at write time and buys cheap, stable reads. The journal pays at read time and in the background, and buys writes at the speed of the disk itself. Which brings us to the interview moment. Which storage engine would you pick? The winning move is a question back. What is the read-to-write ratio of this workload? Watch the mix decide it. When writes dominate, metrics, events, logs, a fire hose of ingest, the log-structured engine wins on pure physics, appends beat seeks. A good rule of thumb, when writes outnumber reads 5 to 1, reach for the journal. When reads dominate, lookups, scans, mixed transactional work, the B tree wins. It prepaid at write time, so every read is cheap and predictable. And now the closing twist. Lift either engine up and look underneath. The B tree database keeps a write-ahead log too. Every serious engine appends the write to a log first, then updates its structure. Durability by sequential append is the cheapest honest guarantee a disk can offer. Two rivals on top. The same log underneath. So, one last time, drop a single write into both machines and watch where it goes. The binder walks down and rewrites the page in place. It pays now. The journal appends, sorts in memory, and merges later. It pays later. Read amplification is the journal's bill, and Bloom filters keep it honest. Write amplification is the tidying's bill, and compaction debt is the storm to watch. Keep the phrase, write in place and pay now. Append and pay later. And when someone asks you to pick, ask the workload. Do the writes outnumber the reads? That one question picks the winner. See you in the next one. Want to keep learning? Come find us at academy.rudewrite.com.